a description of technological change using a Cobb-Douglas production function, which is it's not the only production function we might use to characterize technological change, but it's really it's a standard workhorse sort of production function that's used in economics, both at large scales, as I said, for modeling output for an entire country, also at very small scales, the output of a particular farm or a particular firm. Okay, so I want to do some math here for you using this particular example. So we've derived an expression for the marginal rate of technical substitution for a general production function. I want to go ahead and play some more with this particular Cobb-Douglas production function. So let me pull that down and go through that bit of math. So we start off with the same production function I have here. So output is equal to a technology parameter times labor raised to the alpha times capital raised to the beta. That's just what we had before. I want to go ahead and compute the MRTS. And so you can't quite see it, so push the board up high enough. From this, recall that the MRTS is equal to this ratio of marginal physical products. So I'm going to take a shortcut here. I'm not going to go through and sort of rederive the expression for the MRTS that I did earlier. I'm just going to go ahead and compute the marginal physical products of this production function and then get a ratio of this marginal physical products because I know that's equal to the marginal rate of technical substitution. Okay, so my job then is to compute the marginal physical product of labor for this production function to begin with. What will that be equal to? Just equal to, that would be an A, that's true. What else? An alpha, I like to do it this way. What else pops up here? So we get alpha, A, L to the what? Okay, good. And K to the beta. Okay, that's good. We're also going to care about the marginal physical product of capital. So that's equal to dy dk. And this is a case where probably without even doing any calculus, you can tell me the answer by sort of a symmetry argument. What's the marginal physical product of capital here? Good. So the alpha becomes a beta. The A is the same. We have A, L to the alpha, and K to the beta minus 1. Okay, very good. All right. Now, from here, we can go ahead and just, now we can do the general case. Let's in fact let's do that. So the marginal rate of technical substitution for the general case is this ratio of things. So it's alpha divided by beta. The A's cancel out. That's interesting. And we'll have L, well, I'll go ahead and write it out. L to the alpha minus 1 divided by L to the alpha. And we'll have K to the beta divided by K to the beta minus 1. And so that simplifies. What do we get? I've got alpha L's here on the bottom and alpha minus 1's up here on the top. So I'm going to get, from this I'm going to get 1 alpha in the bottom, yeah? So the L alpha's canceled, is that clear? And a similar trick for the capitals. So I've got one fewer K's here than I do on the top. So I got capital up here. Yeah, so this is equal to the marginal rate of technical substitution. Okay, so a couple nice things happened here for us mathematically. First of all, we don't have any exponents kicking around. All these, the alpha and betas and the exponents canceled out. They still show up here. This ratio shows up, but it's just multiplicative. There's no exponentiation going on. There's also a quantity here. These are parameters that we think are the technology we're operating. We don't think are going to change. So I should make a note of these things. So things to note about this. First of all, there's no alpha or beta in exponents. Second of all, what else does not show up in marginal rate of technical substitution? A is gone. The MRTS doesn't depend on A. And the third thing I'm going to notice about this is a really nice feature is that this ratio, K to L, it has a special name, but not so special you can't guess it. It's called the capital labor ratio. And it shows up all the time in national income and product accounting and sort of analysis of the operation of firms and so on. You can think of it as sort of the amount that a firm or a country has in terms of its total physical capital per worker. So it's the amount of machines or whatever per person operating machines is we'll interpret as that's going to be the capital labor ratio. So, and that's a sort of critical parameter in theories of economic growth that I won't dwell on. But if you take a macro course with anything about growth, you're going to see this thing pop up there. Yes, sir.
So are these three observations general for all functions?
No, so this is all it's true for any Cobb-Douglas production function. Yeah. So the key variable here is my third observation. The key variable is capital labor ratio. Okay. And yeah, this is peculiar to the Cobb-Douglas production function with capital and labor, obviously. All right. Okay. One final thing I want you to notice about this: we didn't have to assume to get this nice form. We didn't have to assume constant returns to scale. This is true even if we have increasing or decreasing returns to scale. We just have general alpha and beta here. We haven't needed to assume that those things sum up to 1. Okay. That's the final point to notice. Okay. All right. So let me change slides on you here for a moment and say a couple more things about this Cobb-Douglas production function, which we're going to see a lot. We're going to see, just like you saw utility functions that have this logarithmic form a lot in the first half of the course, you're going to see this Cobb-Douglas production function a lot in the second half of the course. It's again, sort of a standard workhorse production function that empirically does okay in a lot of settings, and it's also very easy to work with, so it has that nice feature. Okay, so some other things to notice here. The first thing is really a question. With this marginal rate of technical substitution, with this Cobb-Douglas production function, what happens to output if A increases? What happens if A increases? What happens to if A increases? Oh, yeah, sorry. If A increases, then output increases proportionally. It's not going to affect. You can see we already made this point. The marginal rate of technical substitution isn't going to be affected at all. What that tells us in terms of a graph that I'm going to draw for you. Let me see if I can. Let me do it down here. This might be useful to do. So let's go ahead and we'll stick with the Cobb-Douglas production function. Okay, so that's our production function. We've worked out the marginal rate of technical substitution. Sorry, I don't want to do that. Let's think about a couple other things. Namely, how does this thing behave? What do the other factor returns look like? So total physical product for labor here will be equal to what? That's almost a trick question. It's the same thing. We're just going to hold k fixed at very L. So if we do that, I'm going to draw this. I'm going to draw this function over here. So it's just equal to AL the alpha k to the beta. But we're only going to vary L. If I were to draw the total physical product of labor here, what would it look like? It's got an exponential thing. That's right, for sure. Let's see. Let's start with labor 0. What's total physical product? Yeah, so 0. So we got that one for sure. And then as you say, it's going to increase in an exponential way. It's going to be convex or concave. It's going to depend on alpha. If alpha and beta sum to 1, that means that alpha can't be greater than 1. So if alpha is less than 1, how is this thing going to increase? At an increasing rate or a decreasing rate? At a decreasing rate. So, for example, alpha is equal to 1/2, we just get this would be a square root function, right? So this is with alpha less than 1. Okay, and this is to say the total physical product. All right, we've already worked out what the marginal physical product of this function is for L. I think I haven't erased it. Let's see. So we said that the marginal physical. Oh, I did erase it. Okay. Oh no, it's up there. You can see it better than I can. So the marginal physical product of L we already computed. It's just equal to the slope of a line like this, and that's in this case equal to alpha a L to the alpha minus 1 times k to the beta. And how about the average physical product of labor? So to get the average physical product, we divide the total physical product by L. And so that's exactly right. We get A k to the beta L to the alpha minus 1. So the average physical product in this case is going to be equal to the marginal physical product, except scaled by the constant A. So look, these are exactly the same, except for this proportional thing A. This is a consequence of the homogeneity of this function. This relationship between the average physical product and the marginal physical product definitely doesn't hold true for every production function. It's this sort of magic is happening because of the homogeneity we have in this function. Okay. Let me draw this for completeness. Okay. All right. So that's the Cobb-Douglas production function. Here are different factor returns: total physical product, average physical product, marginal physical product. Yes. Which? Oh, thank you. Yeah, I have it on the wrong one. Thank you. Yeah, that's the point I was trying to make. In fact. Okay. So we have the factor return for this: the different physical, the total physical product, the marginal physical product, and the average physical product. We've noticed that the marginal rate of technical substitution does not depend on A. If I were to draw a graph of labor and capital like this, I had some, isoquant, an isoquant like this. Let's actually try this. So let's say that y is equal to 4 on this isoquant, as we did before. Yes.
So here's the y-axis y.
It's total output. That's right. So the height of this function gives us the total physical product. This is TPP, and the average and marginal physical product are given by slopes of the ray or the tangent to the function respectively. Are there questions about this? Okay. Okay. So let's do a little experiment now. Let's imagine that we have I'll do it in a different. I'll do it here. So let's do this experiment. Let's take this Cobb-Douglas production function, but in case we're going to have two cases. In the first case, we're going to let A be equal to 1. So let's say that's the case we've drawn here. And then that's case 1. And in case 2, we're going to let A be equal to 2. Okay, so in my drawing, what happens when we... So, and I want you to think of this as a technological change. We've got a technology which is twice as good at transforming inputs into output. So it's a technological improvement. So if we double the value of A, what happens to this figure over here? Well, it gets steeper, right? I mean, the total physical product still starts at 0, but it's going to be a curve that's going to be, at any point, the slope is going to be twice the slope of this one. You can see that A shows up here in the marginal physical product, so the marginal physical product at any point doubles. The average physical product at any point doubles, which is why we say that the total factor productivity of the function will have doubled. That's the TFP, our total factor productivity we talked about earlier. So let's let, this is the case where A is equal to 1. So I got an isoquant here from the old inferior technology where A is equal to 1. And let's imagine that, now use the same inputs, but produce Y equal to 4 with the new technology. What's the isoquant for the new technology look like for output equal to 4? So Tom says it shifts down. That's okay, so why? Yeah, so I can produce, that's exactly right. So pick a point, any point really on this curve. If I'm producing 4 using, let's say this is 2 units of capital and 2 units of labor, I can now produce the same amount of output with 1 unit of capital and 1 unit of labor. So I'll get a new isoquant for a different technology. This is a different production function. This also has Y equal to 4, but this is with A equal to 2. So it takes less resources to produce the same amount of stuff. So that's a sort of technological improvement. All right. Maybe I'll note in passing, I've drawn a 45-degree line here and said if we have stuff, we're going to have to think. That's true if I've drawn the curves correctly for any line I draw through here. Any ray is going to have the feature that this is going to use half as many resources as this. Yes?
What would happen if there's technology that only improves the efficiency of one input?
Okay, so that's a good question. So certainly technological changes that affect the productivity of one input differently than another exist. If you wanted to model that here, you wouldn't do it by changing A. I got this argument here on this slide, I think. Technological changes that don't change the marginal rate of technical substitution, like this change in A, are called Hicks neutral technological changes. And so if we had a technological change that made labor more productive relative to capital, for example, that wouldn't be Higgs neutral. We can model, let's look at this projection function. Could we model that here, do you suppose? What might we do differently? If we had something that made labor more productive but didn't make capital more productive. Yeah, so graphically what we want to do is we'd have a change in the slope of the isoquant. So what we do is we'd wind up with something that was shifted this way. So that would give us a shift like this. A change the slope like this would give us a change that favored, that made capital more productive. Mathematically, what could we do here to get an isoquant like this that would shift its slope? Notice, so let's pick a point here for L. Notice what's happened is, if I draw this, maybe didn't draw it very well. So that the steepness of the, let me do this mathematically. Remember, the marginal labor technical substitution here between labor and capital is equal to alpha over beta times the capital labor ratio. Okay, so if we had a technological change that substituted towards having us use more labor because it made it more productive, what parameter could we change here to make that happen? Yeah, labor share alpha. If we jack up alpha, that's going to increase the slope of the indifference curve in the way we want. So the marginal rate of substitution, here is greater than it is here if I draw this correctly by increasing alpha. So change in alpha or beta would be an example of a technological change. It was not Higgs neutral. That's something I'll try to return to in an example a little bit later. Okay. Are there other questions about this? Okay. Okay, actually I've got a, rather than using my not so elegant graphs on the board there, I've got a picture of what happens if we increase alpha. So these again are the same, these are two different cases. The case on top is a case where alpha is equal to 1/3, this is the case we graphed earlier. And then imagine a change in technology so that we increase alpha so that it's equal to 0.5. These two curves may look similar, but if you look at where they're tangent to this green line, it has the same slope, there's less labor used to produce output of 4 than there is in this case. Is that apparent? If you use a ruler, at least you can draw through here and say this point lies to the right of that point up there. Oh, maybe that's a better way to do it. Oh, yeah, yeah, I agree. Maybe because the k-axis is compressed here. All right, so I'm going to next share a little example with you. So this, the figures I've got here, I'm going to be using for the next little bit, are drawn from a paper by Fugli written in 2008 in Agricultural Economics on changes in agricultural productivity over the last 50 years. And so the first thing that Fugli does is, so I'm going to try to describe some of those changes, and we'll talk some about how agricultural output has changed for the world, and we'll also talk about whether that change in output is due to increases in, it can be due to one of two things. Increases in output, which we observe, can be due either to increases in the input supply, so increases in labor and land and so on, or it can be due to improvements in the technology people are using to turn land and capital and other agricultural inputs into output. So it's either going to be a change in technology or an increase in inputs that produces increases in output. Okay, so first of all, what Fugli does is he decides on a model for the agricultural technology that people use. He's doing this. These figures are not actually using aggregate data. They're using farm level data, and these are drawn from different papers. So there's a paper that uses data on farms in India, for example, a different paper that uses data from Indonesia, farm level data, to estimate these numbers. These numbers are all shares of the sort that we're talking about. So this first column in particular is the labor share parameter we've been talking about. He doesn't. He breaks up what we've been calling capital into some other components. So we're not going to have k kicking around by itself in this example anymore. Instead, what we're going to have is labor and a bunch of different other inputs, which we might call capital services. We're going to call them by the names that are given there. So output here is going to be a Cobb-Douglas production function. So that's the total value of agricultural output from these farms. It'll be equal to some technological parameter A times labor raised to, we'll call this alpha. And then there'll be, these are familiar. The next thing is we want to look at is this next column. This is buildings and land, mostly land. The buildings are mostly not so important here. So land is being treated as an input here. So I'll call that land, in fact. So that's raised to a number I'm going to call beta sub 1. There's also feed and livestock. So this is agricultural production includes both row crops and grains, but also cattle and pigs and so on. So expenditures on feed and livestock, let's call this feed.